Okay, yes, good morning, everyone. How are you doing? It's pretty cold. Okay, today we'll talk about a couple of things. We'll talk about formula of total expectation called conditional expectation. We'll talk about generating function and probably about inequality. There are plenty of things. So let's start. Here is first question. It's useful question, interesting question. It uses some interesting property, some kind of Markov property. It's about trapped minor. Please read it. And we start to solve. Okay. Let me use for this question our new slide notes. Probably it's quite a bit of yes. So we have a minor in a mine in the room, and the room has three doors. One door leads to his home, to safety, after 3 hours. It's good door. It's very good. Two additional doors leads to the same room. Door number 2 refers to the mine after 5 hours. And the door number 3 returns to the mine after 7 hours. And this miner has Alzheimer. He did not remember which door he chose. Okay. So every time he selects one of the 3 doors uniformly. 1 divided by 3, 1 divided by 3, 1 divided by 3. Okay. The miner is equally likely to choose any door. And we want to find in the first question, in the first part, the expected time until he gets home. Until he returns to his. This is the question. Okay. The question is clear? It's interesting question because his travel can be infinite. Yeah. Every time choose this door, again. Yeah. It's a very interesting question. Okay, so let us denote.
And every time he returns to the mine is
So the same room.
It's independent, right?
Yes, independent and memorable. He didn't remember which door did he select. Yes. He has Alzheimer. He didn't remember anything. Okay. So let us denote by X his traveling time. And our goal is to find the expected value of X. Make sense? Okay, as usual, you can say, let us find expected value of X by definition. It equals sum X goes from, in general, 3 to infinity, X probability that X equals X. Why X starts from 3? What is X was? He said traveling time. It's traveling time. How many times he wins until he gets safety? كم زمان وصريح أشو مجيبايت.
X is 3 because the shortest amount of time is 3.
Yes, because
3 hours.
yes. And pay attention, for example, probability with x equals 4 equals probability with x equals 2, for example, yes, equals 0. Because it's impossible. Yes, it's impossible. And probability with x equals 3 equals, what is the probability that he will return home after 3 hours of traveling?
1/3.
1/4. 3, yes, 1/4. It's easy. But what is the probability with x equals 100? There are many possibilities. He can choose sometimes Vizdo, again, Vizdo, and after that he needs to return. There are many possibilities. It's not very easy to calculate with probabilities. It's complex expression. If you want to find this guy, it's some kind of some number power n
Yeah.
plus some other number power n. You can find a human generating function, but it's not very easy. Yes, times some other constant. One, it's not very easy expression. So, if you want to find expected value using definitions, Cumberstone is very, very messy. It's very messy expression for this guy. For probability with x equals k, it's messy expression. You can find it using generating function or difference equations, if you like, difference equations. And afterward, you need to substitute this guy to this formula. And it's very, very cumbersome. It's very, very long. We can do it for this question, but it's very cumbersome. And we need to know additional things as difference equation or generating function. So it's not, it's a bad solution. It's long solution, it's a messy solution. So we won't use, okay? But it's clear, yes? What we want to use? We want to use a formula of total probability or a formula of total expectation. Okay, this is our sample space. And we want to find the expected value of x. And as we saw, it's hard, yes, we don't know, it's messy, it's hard. And the idea of a formula of total expectation is similar to the idea of formula of total probability. We divide by our sample space using other random variable, which you have, for example, y equals 1, y equals 2, etc. And we calculate the expected value of x and expected value of x given y equals 1. Divide and conquer. Spread them short. Okay. Instead, calculated expected value of x. We divide the conditional the value of x by some helping random variable y. After that, we find this conditional expectation. And after that, we find the expected value of this conditional expectation.
Isn't this the iteration, the iterated of something? When we have the e of x equals to e of x, given y,
It will.
isn't this the same equal? The inside.
This yes.
The second, yeah, this isn't this equal to e of x?
Yes. E of x equals to this guy.
No, the second e isn't this equal to e?
No, it's equal to e of x given y equals 5.
Yeah, no, it's equal to e of x.
No. It's expression.
So this is way.
Without it, no, it's incorrect. This is correct expression.
Because I've seen before something like e of x equals to e of x given y.
No. This is the formula. Where is it?
E of x.
No. This is conditional expectation. Yes. This is conditional expectation. And if we pay attention, this formula is a function of y. But expected value of x is not a function of y, it's a function of x, of some number, sorry. So you need to expect to integrate it out. So we want to use something very similar to the formula of total probability. It's the same thing. So we want to find to using the formula of and now you will see something interesting. We will solve this complex question about expected value It's complex question. If you won't use the formal conditional probability, conditional of total expectation, it's messy question. But using conditional expectation, we'll solve this question in one line. Instead of difference equation, we will get linear equation, one linear equation. And we will find solution immediately in one line, one-liner solution. Okay. Are you ready for this? Yes? Yes. Okay. Let's see. So, we need to condition by something. Oh, here we have many choices, infinitely many choices. How we can conditional for what is our helping variable? Why? Okay, the minor, his first step, he need to select the top. Yes. Let us conditional x by the number of door which he select. This is the trivial thing we can do. Yes. So we will find the expected value of x given y equals y when y is the first door chosen. It can be O1, O2, or 3. So by the formula of conditional expectation, expected value of x equals expected value of x given y equals y for y from 1 to 3 times probability with y equals y. That's all. It's very, very similar to the formula of total probability. It's the same idea. Exactly same idea. Okay. So the transition from here to here is clear. This is important step. Oh. Please help me to calculate this guy. What is the probability that in the first step, the minor will select some given door? But first one will be one. Exactly, 1 over 3. Why? Because it's given uniformly. He select any door, the probability 1 over. It's clear? Okay. Please help me find expected value of its travel, of its travel time, given he select this door. What is his travel time? If he select the first door, he goes home after 3 hours of traveling. Very simple, it's simple. So expected value of x equals 1 over 3 times plus. Let us think about next fellow. It's very, very important thing. What is expected value of x equals y given y equals 2?
Right, that's fine.
Yes. Let's see. First of all, this minor goes 5 hours. So it equals 5 plus something, plus continuation. Now, he made his traveling and he forgot about anything. He started again from the same point. And again, we want to find expected value of his traveling until he gets safety. But we have notion for this. It's E of y, of E of x, sorry. The process restarts itself from the starting point. It's some kind of recursion. If you like recursion, computer science or mathematics, it's recursion. After returning to the same room, the process restarts itself. Yes, the same conditions. Pay attention. We have here some kind of linear equation. So expected value of x equals 1 over 3 times 3 plus 1 over 3, 5 plus expected value of 3. And what you can say about expected value of x given y equals 3?
7 plus 7 plus
Yes. 1 over 3, 7 plus. You see, we have one linear equation. Can we solve this linear equation? Yes, one linear equation about a known variable. It's very simple, yes? We solve it. And we get 3 plus 5 plus 7, 15. One line solution. Okay, there are many things we need to understand, yes. But in general, one linear equation solves this question. Instead of using different equations, cumbersome sums, anything else, this is solution. So in average, the miner will spend in this labyrinth about 15 hours. It's amazing solution because hard questions turns to very simple question. It's not very simple. Okay, you need to understand it. You need to solve a similar question. Yes, you need to think about it, but the solution is very, very beautiful. Instead of difference equation, we get linear equation. And very, very simple equation. In average, you will visit every one of those and it's 15. Okay. So this is a very powerful technique. You know, probably know it from computer science. Divide and conquer, formula of total probability and formula of total expectation. Instead of solving complex question, we divide it to 3 simple questions and we solve. Okay, it's clear? Yes, it's very wonderful question. Let's see what we have here in addition. Here you can find explanation.
Yes. I'll put this somewhere in one of the chapters. Where would that be?
At the bottom. Expected text and expectation. Yes, expectation. Okay, and here the explanation, if you want to read it, after that, it's okay. Did you speak about generating function with Fourier? Yes. Okay. We won't speak about this now, but in general, the moment. Okay.
We talked about the function generating function.
Probability generating
Yeah,
function.
the expectation, and then the characteristics.
Characteristic function, yes.
We didn't talk about that.
We don't need the characteristic function today. Yes, it's complex numbers, it's a bit cumbersome again. Okay. Additional solution to this question, we can find it using generating function approach. Okay, generating function for this process pattern is very, very similar. With probability 1 of the 3, he goes only 3 kilometers. The value from the variable is 3. Yes. With probability 1 of the 3, he goes 5 hours, sorry. And the process restarts again itself. So we have the same generating function. With probability 1 over 3, he goes for 7 hours, and the process restarts himself. You see, it's very similar to idea we saw in this solution. And now again, we have one equation with one unknown generating function. Solving this question, we can find generating function. This is a generating function for this process. And in general, we can find the first derivative of this fellow and at x and substitute y, and we get expected values. This is next solution. Right, okay, it's next solution. We'll talk about generating function next time, but this is a given solution. As you can see, it's very similar to the previous one. But instead of expected values, we have generating function. But what is generating function? It's expected value of something else. So you can see it's very, very similar. But here we need to find derivative. In the previous solution, we don't need to find derivative. G of 1, a derivative. We need to find just one. First derivative, substitute x equals y. Find expected y. So, generating function is all very powerful ones. We talk about it today, not for next time. So it's also very important. Okay. So we can find probability generating function for this random variable. We can find its first derivative, substitute x of 1, and we get expectation. For example. Generating functions, as I said, very powerful tools. They exist courses in mathematics faculty in our university, the Tufik Mansour, where we study generating function all the courses. There are two courses, 1 and 2. Why? Because it's very powerful tools. It's related to transform Fourier, to transform Laplace. So there are many useful transforms. Okay, we studied only one lesson, but it's very, very powerful. Let's continue this question, but I need to return to my old slides. Okay, this is the return. Okay. Okay. So, okay, we can find those derivatives, substitute 1 and get 15. Oh, something interesting. How we can find probability? What I asked you previously, when x equals 100. Okay, there are many combinations, yes, probability, okay. But if we have generating function, if we found generating function, we can find probability with x equals k for any integer k. How? Okay, the idea is very simple, but the realization is not very simple. For example, to find probability with x equals 100, we can take generating function of x, find the derivative 100 times, and substitute x equals 1, z equals 1, sorry, x equals z equals 1, and divide it by 100 factorial. It's Taylor kind of, it's Taylor series. You have function, and you write an expression to a Taylor series. And the coefficient of every x power z power k is a probability that x equals k. It's a basic property of probability generating function. Okay, what is property? It's a good question. What is a j x z? It's the perfect value of equals sum, yes, x grown from 0 to infinity, probability x k. X equals k, z power k. So the coefficient of z power k is a probability, but you need to normalize it by k factorial. Okay, but how we can solve this question? Not by hand, yes. We won't find 100 derivative of some function. You are right. We can go, for example, to maple or to Wolfram alpha, and we can say to it, please take our generating function and find 100 derivative of each line, and we get the desired value. That's all. It's simple if you have computer. It's not so simple if you don't have computer. But it's possible. In general, it's possible. So here you can find probability. Okay. It's clear? Okay. Okay, let me explain how we can find probability generated for function of x if we in this slide, in this question. Okay, so let us find probability generating function of random variable x. Okay, by definition, it's equals to expected value of z power x. It's a definition of probability generating function. When it's defined, it defines for integer non-negative random variables, only for z. But in our question, x is integer non-negative random variable. Why it's not negative? Because it's duration of traveling. Why it's integer? Because each of the doors leads to the tunnel 3, 5, or 7 kilometers. It's integer. Okay. How we can fight this failure? The approach is the same approach. The generating function of x at point z equals expectation of z power x. And again, we use the formula of conditional expectation. Similar way. It equals expected value of zx given y equals 1 times probability y equals 1. It's 1 over 3, yes? Plus probability of z power x given y equals 2 times probability y equals 2, and we continue the same way. The idea is the same one. And how we can find this expectation? Let us see. Oh, let's start from this field. If y equals 1, he goes home after 3 kilometers. Here we have z power 3, x equals 3. So z power 3 times 1 over 3. Pay attention, the power of vz is a x, it's 3. What we have in this case? In this case, the miner goes 5 kilometers, z power 5, and the process restarts itself times gxc. And the same things here. We have linear equation for generating probability generating function. We solve it and we find PGA. Again, using recursion. So this is PGA. You know, if you specialist in probability generating function, you can get final answer immediately. Why? How? This is last step, yes? Last step of this traveling is 3 kilometers, probability 1 over 3. What we have here? 1 divided 1 minus 1 over 3, z5 plus z7. It's equals to 1 divided by 1 minus q. What is inside? It's geometric series. It equals sum q power I from C. Yes? So we have here in how many, whatever number of these steps. Yes, and after that he need to make his last step. So this solution is very obvious if you study generating function. Time it's very obvious. You can guess it immediately. Oh. Suppose we want to find variance of x. We won't use definition. Yes, it's messy. How we can find variance of x? Oh, we can use second derivative, or we can use the formula of conditional variance. Okay, we won't use it here, but it's possible. Here we can find if we found previously generating function of x, variance of x equals second derivative of generating function of x at point 1 plus first derivative of generating function of x at point 1 minus second derivative of, minus square of first derivative at point. It's already formula. Yes. And again, if you solve this question at home, for example, you can use computer to check yourself about derivatives. Yeah, if you need to calculate derivatives, you can use computer. Yeah, you know, today we use computer very, very broadly, and it help us to find derivatives, they were expression or integrals. Okay, let me summarize. Generating function, all kinds of generating function, probability, Laplace, characteristic function, cumulant function, there are many of them, very useful tools. Why? Because we have nice properties, we help us to summarize all distribution, all information about random variable in some kind of in one function. It can be rational function, it can be square function, it can be trigonometric function, but this summarizing all distribution in one function can be very, very helpful. Did you talk about Markov inequality? Not yet, or
We have to learn it by ourselves.
by yourself? Okay. But the question is, did you do it? No?
Yeah, I mean, I almost
Close. Okay. Let's talk a bit about two useful inequalities. It's a good question because it's summarized many things. Okay. Inequalities. Why we need inequalities? Yes, there are many inequalities in computer science and statistics, machine learning. Markov inequality, Chebyshev inequality. There are many. Cherno inequality. There are many of them. We can also talk about all of them today. All of these inequalities help us to estimate or to bound probabilities of some of them. For example, probability that x less equal something should less equal something else. This kind of probability. The first question is, you can ask me or yourself, why we need inequalities? Why we need such things? Why we need inequalities? Because in many situations we can't calculate probability exactly. Sometimes it's very hard to, impossible. Okay, if we don't know how to calculate these probabilities, the best thing we can do, find some bound on these probabilities. Yeah. So inequalities is useful tools. Sometimes they help us to bound from below, from above, the desired probability. So it helps us to prove theorems, to estimate probabilities. So it's helping. Again, if you know how to find the probability exactly, and it's not hard way, it's easier, you don't need inequality. But in many situations, we don't know. So we can use inequalities. Okay. And as you understand, if you want to estimate some probability, there are infinitely many inequalities. Yes, you can say, oh, probability, n equals 0, so less equal 1. Okay, it's inequality, yes, but it's useless. It's always correct. Any probability between 0 and 1. So we want useful inequalities, not some inequality. We want useful inequalities. Okay. One of important simple inequalities is a Markov inequality. It tells us that x is non-negative random variable with probability that x greater equals a times its expectation less equal 1 divided by a. Very simple, very useful inequality. Probability that random variable, non-negative random variable x greater equal a times expected value of x less equal 1. It's very quick, but it's useful. Let me demonstrate you this idea. Suppose x is a height of random person. Oh, what we know about expected value of x, I don't know. Let's assume that 175 centimeters. Okay. Please help me estimate probability that we will meet now outside the man or woman with height greater equal 2 times 175, 3 meters, 3.5 meters. Why? Yes. Why? Yes. But okay, but what you experience say to use? What is the probability to meet now men with height about 3 meters? Yes, it's not very tight. Yes, it's not very. In this situation, it's not very helpful. We know this probability almost 0. Yes, 0.00001. Okay. So Markov inequality is not very tight in some cases for this question. But we can't improve it. We can't prove that it's impossible to improve Markov inequality. How we can prove it? We can provide example such that for this example, Markov inequality turns to equality. And this equality is impossible to improve. So, okay, let us use Markov inequality to estimate probability that traveling time of this miner creates minus 100.
Actually, we voted definitely by.
There are two kinds, but it's the same. Yes, yes. Something you can write it, you can move it from here to here, but it's the same thing. Yes, it's the same. Oh, you are right. There are two forms, but it is same. It's exactly the same. But this form I like it better because it says a greater equal than its expectation times something. But again, yes, we can move it in this stuff. But as we say, I usually write 2 for my lectures, okay? But it's the same. Well, so let's return to our
So what
question.
was your formula? It's exactly like,
Okay, this is the first form,
yeah, equals.
probability, but you need to check it in the form. Where equals A, less equal expected value of A divided by A. This is same. Yeah, sure. You can denote A by V spell and you will get this result.
So the probability that x is great equal to 100 is less than 15 over
Yes,
100.
yes. About 1/6, about, yeah. Approximately, yeah. Probably 1/7. And pay attention, this probability, it's very, very small probability, where is our Taylor explanation? This probability is very, very small. Okay, we use inequality and we get some approximation. Here 2 forms. Here 2 forms. Here I will get. Yes. But sometimes Markov inequality is quality, it's tight, it's excellent. But in many situations, it's very, very not exactly. It can very mad cast. Not cast. Okay. So this is Markov inequality. It has 2 forms, it's the same thing. Probably this is more useful, but this is easy to understand. The probability that random variable x great equals its expected value times a, less equal 1/a. Okay. Make sense? Okay. And if we talk about Markov inequality, let us use Chebyshev inequality. Have a time? Yes, have it. Okay. We can take Markov inequality, and using Markov inequality, we can prove Chebyshev inequality. Also, it has 2 forms. This is one of them. And it's correct not only for positive random variable and also for any random variable. We find variables. Okay. What is the meaning of Chebyshev inequality? There are 2 forms. Yes, you can move this value again here. It says the probability that random variable x minus its expectation, absolute value of this difference, great equals k times its standard deviation, less equal 1/k squared. This is Chebyshev inequality. And the question now, we want to estimate probability that x great equals 100 using Chebyshev inequality. Is it better than Markov inequality? Not always, it depends. But in general, we use here 2 things. We use the information about expected value. We use information about standard deviation. It can be better. In many situations, it's better, but not always. Okay, so our goal is to estimate probability that x great equal 100 using by Chebyshev inequality. It's a technical solution, but it's important to understand. Are you ready? Let's start. Oh, probability x great equals 100. You see, we can't use now Chebyshev inequality because it doesn't have the same form. Yes, the form is absolute value x minus expectation. It's different. So our goal is to move on through the steps to approach the same form. Okay, first thing we need to find minus expected value. Yes. Okay. So we move 15 to this side. Probability that x minus 15 great equal 85. This expression equals to this expression. Make sense? Why we do? Because it's similar to our final Chebyshev inequality. Okay. Okay. Now what we want to do? We want to put absolute value. We can do it, but we need to pay.
Examine some.
Yeah. Probability with x minus 15 greater equals 85 less equal probability with x minus 50 greater equals 55 or second side. Why is this inequality correct?
Because we are thinking two cases.
Yes, probability of A less equal probability of A union B always. That's all. And now we can unify this and this level. Yes. It equals probability with absolute value of x minus 15 great equal 85. And now it's almost the same form, yes. Almost the same form. Okay. We can write 85 in this form. We need to decompose this number to these factors. Square root of standard deviation times this constant. This is standard deviation. And now by Chebyshev inequality, we know this probability less equal 1 divided z number square. 21 divided 25, something 26, 7. Okay. So this is our estimation for probability with random variable x greater equal 100. It's better, yes, when the Markov estimation. Yes, in this question is better. But it's very far from real answer. Real probability is very, very small now. Next question we can ask, is it possible to improve Chebyshev inequality to make it better? And the answer is no, it's impossible to improve Chebyshev inequality because it's time. How we know it? We can build example, we can build random variable, such that inequality turns to equality. So it's impossible to improve Chebyshev.
How do we find K or what?
Okay, we want write 85 as something times standard deviation, yes?
Yeah, fine.
And you know this value, it's square root of 201, yes? You solve this question for
Yeah, okay.
you can use second form of Chebyshev inequality. There are two forms. The second form of Chebyshev inequality says the probability that x minus expected value of x, absolute value, great equals k, plus equal, I don't remember exactly something. Yes, you can use second.
Okay.
So, here. By Markov inequality, we get estimation probability that x greater equal 100, 0.15. Using Chebyshev inequality, 0.043. And this is exact answer. It's much, much smaller. Make sense? Okay. Okay, let's see what we have. And stop. Is somebody in the Zoom today? I see. Okay. Okay, I published yesterday, but you have 2 weeks. The homework number 6. Probably there will be 7 homeworks. Yes, I think this week and 2 weeks you get 7 homework. It's the last one. Okay, 7. So if it's 7 homeworks, it's enough to submit 5, something like that. Okay. So I published 6 homework and also I published solution to 4th homework. Okay. Where is it? Here. Yes, you can find solution for homework number 4. Okay, again, please read our slides until the end. There are many interesting questions with solution. The solution is not obvious, but the questions are important for you to understand. As usual. Okay, next week we continue. I will review. We will talk with you about probability generating function, and we will move on. Yes.
What do you do with delayed homeworks?
What do you mean? It's okay, but in general you don't need it because it's okay. But in general you don't need it. You don't need it because it's enough to submit 5 homeworks from 7. But 1 day or 2 days it's okay. 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 So thank you. I'll see you next week.